Hello and welcome. This is an overview of lines in the plane. In this lesson, you will learn how to find and use the slope of a line to write and graph linear equations. You'll learn a little bit more things, but that's the basic thing. All right, I built this nice, big, elaborate looking thing here. They all mean something. Here are all the different equations, formulas, uses, advantages, conversions, meanings, assignments, and restrictions for these three different forms that you might be graphing a linear equation. Okay, now where to start, right? Standard form is something that you actually don't use all that much when it comes to graphing. There are some benefits to it, like when you're solving for intercepts and setting up some word problems. I'll make sure to give you that. Most of the time you're seeing integers here. A is going to be a positive integer. That's standard form. Okay, slope-intercept form is something that you can get to by solving for y, getting y by itself from standard form. You'll go and get there. Y equals mx plus b. M is the slope, b is the y-intercept. That's something that you've probably seen for a long time. We're going to learn how to graph without a table using that way just as well, and just with all the other ones as well. Point slope form's right here, but let me back up a little bit for that one. First of all, slope is rise over run, or the change in y divided by the change in x. The larger the value is, the more steep that line is going to be in the positive or negative direction. You got negative 100, that's going to be super steep going that way. Anyway, change in y and change in x. You have x1, y1, x2, y2. We've talked about with right triangles before how the distance between these two things is the difference of these two things. And the distance here, x2 minus x1, y2 minus y1. The difference is we're not solving for the distance between them anymore, in between these 2 points. We're just trying to find out how much it rises over how much it runs. It rises that much, it runs that much. Here's the ratio. It is just some rate. x2 minus x1 could not possibly be 0, otherwise you'd be dividing by 0. That is why vertical lines have an undefined slope, because you'd be rising infinitely, or just some amount, but you'd be running 0. A slope of 0, however, is with no rise, and that's possible to have. Okay, now what does this have to do with point slope form? Because take a look at this, the equation right here. What if you multiplied both sides by x2 minus x1? All right. Now, what I'm going to do, though, is I'm going to ignore the x2 and call it x, ignore the y2 and call it y, because in point slope form, we don't know 2 points necessarily. You know 1 point. And you know, or you can calculate the slope. So what you're going to do is you're going to choose one of your 2 points, substitute it into here. Now, why did I multiply both sides by this? Well, check this out. y2 minus y1, or y minus y1 in this case, is m times x minus x1, x2 minus x1. So that's where it comes from. If you have trouble, memorizing it, whatever, that's what it looks like. And what's actually interesting about this one is it's the first one that you're not looking at a y equals for. You know, when we had y equals x minus h plus k kind of stuff, this time your minus k, or your plus k is actually over on this side. Why they choose to do that? Not sure. Maybe because they both have y in it this time. But that's how you generally read it. Do I personally like point slope form? It's okay. We'll use it. M is the slope, and x1, y1 is a known point or solution on your graph. Okay, what are their best uses? Standard form I mentioned, solving for intercepts. I'll talk about that again. Setting up word problems. That's going to happen time to time. Every so often you'll have y equals mx plus b for word problems. But this is my favorite one. It's very small. It's used for graphing. I know what y-intercepts are. I know what the heck they mean. I know how to use the slope stuff. This is equally as good. The difference is you might not be starting from the y-intercept. Instead, you're starting from a different point. There's no problem with that. I think the main issue people have is the minus aspect, because remember the point is x1, y1, not negative x1, negative y1. But no, it's fine. In fact, this can be better when your y-intercept is a fraction and these were integers. So that way you're staying with integers. All right, so that's what you have all around here. Now I'm going to do a lot of examples here. So slope-intercept form, once again, it's y equals mx plus b. Slope is rise over run, change in y over change in x, how they change in that case. Okay. And the y-intercept is the value of y, sorry about that, when x equals 0. It's where it crosses the y-axis. and that is at x equals 0. So that's what the y-intercept very specifically is here. Okay, how do we do this without a table? That's what's being asked here. Y equals 2x minus 4. What I'd recommend, especially when some of them kind of look different, is identify what your slope is. Your slope is 2, or better yet, written as a fraction, 2 over 1. This is how much you rise. This is how much you run. B is at the point 0, negative 4. The y-intercept is negative 4, but it's crossing specifically at this point. So how do you graph? Well, this whole thing is about the slope is how much this changes every time you increase x by 1 in this case. So if I use a known point like 0, negative 4, I can from here rise 2, run 1. Hopefully for the people I'm speaking to with this video, this is something that you've heard before. So I don't want to get this big, huge concept of what this is by using a table to kind of prove what's happening, but I'm just going to do those points there. How many do you need? To be honest, as many as you can fit. That's always my mantra. That's my go-to. Now, we go down 2 and we go to the left 1. Now, what's interesting about that is that that's a slope of negative 2 over negative 1. You fall 2, you run 1 to the left. But a negative divided by a negative is a positive. That's what makes this acceptable. Furthermore, you know this is supposed to be a straight line, so this is what makes sense. All right? And obviously, we're sometimes just all about making sense here. So I'm going to go ahead and graph this one from here to here. Looks great. Use your own straight edge for that. Draw arrows at the end. You have your graph. Okay, let's do it 2 more times. The only difference between these two and this one is, well, this one you don't see the slope as well. What is the number that's in front of x? That's a negative 1. So that's negative 1 over 1. Or negative 1 over positive 1. This is not negative 1 over negative 1. You do not apply the negative twice. Remember, that's a positive number. You can also apply the negative on bottom if you so prefer. Because what you really want to think about is rise and run. If you're rising negative 1, you are falling 1. So I'm going to show you that right here. And if you're running negative 1, you're running 1 to the left. So your y-intercept is at 0, 3. If I rise negative 1, I fall. As I run, 1 over. Down 1, over 1 to the right. Remember, that 1 in the denominator is still positive. So I'm going to run that way. All negative slopes go in a downward fashion like that. Positive slopes go in an upward fashion. Or better yet, as you run to the right, think of it like a timeline, chronologically speaking. As you run to the right, are you increasing or decreasing? That's the question. Now, how does this one help you out a little bit? Well, because you can rise and run 1 to the left, and that's where it kind of shows this display right here. So that's kind of an example of how you can put the negative on one value or the other. But if you put it in the middle, and I've seen it plenty of times, if you put it in the middle, you tend to just call both of them negative. That's a careless mistake for a lot of Algebra 1 people. I believe once you get to Algebra 2, pre-calc and stuff, you're more than okay with what's being said here. But that's a good explanation for it. Okay, passes through the origin with a slope of 1/2. This one's not even an equation, but can you graph it? Well, do you have slope and y-intercept? Your slope is 1/2. They tell you that. Passes through the origin. Now, the origin point is 0, 0. That is the value of y when x equals 0. Y happens to be 0 when x is 0. So you do have your y-intercept. It's right there. So what do you do here? You apply the fraction 1 over 2. You go up 1, you go over 2, you plot that point. You can find points in between, and I'll kind of show you how that works. But you're landing on fractions if you do. Nothing wrong with fractions, except everyone hates them. But you can, CAN, you can do that. Let me kind of show you how and why. If we're all about, you know this too, how I put it over 1? If we're all about putting our slope over 1, you could make your slope 1/2 over 1. What does that mean? It means you rise 1/2 and you run 1. If I go up 1/2, I go over 1. I've plotted this point right here. Nothing wrong with that. It's still a solution to the equation. It's still on the line. These are just as good. Only, what if you're talking about 1/5, right? Sometimes it's just unnecessary, right? If you can deal without the fraction, go ahead. That's good too. And there's your line. So there you go. Slope-intercept form in a nutshell. Okay, standard form. Standard form, ax plus by equals c. Now, the thing about a, b, and c, a is not stretch factor like you learned with quadratic whatever. It's just using letters here. The thing about standard form is that you cannot look at any of these three numbers and just graph it, right? This number is not slope. This number is not y-intercept. You have to solve for y to figure out what it is. In fact, just to prove it to you, Let's go ahead and subtract 2x right here. I know I'm going to an example before I talk about all this stuff, but I just want to show you what I mean by here. Divide both sides by -3, you'll get y equals positive 2/3 x minus 2, which of course you could always graph. But here's your slope, here's your y-intercept. Where were these numbers up here? Okay, -2, but that was just coincidence. These numbers don't reveal anything in your graph directly. You'd have to actually do more stuff to figure it out, which in this case, finding intercepts is very easy to do. The x-intercept, set y equal to 0. The y-intercept, set x equal to 0. What's going to happen in this thing is, thankfully, the only other number you have to deal with is the coefficient in front of the x or the coefficient in front of the y, and just divide. You'll be very settled with that. Converting form, that's what I was doing right here. Convert to slope-intercept form by solving for y. So you may do that as well if you absolutely feel like you must or need to. A reason why you might want to do that is if your intercepts are fractions and not integers. Okay, first example is not even an equation, but this has intercepts. This kind of shows you the example of what you're doing. X-intercept -7, 0. Y-intercept 0, -3. These are 2 points on a graph. This is a linear equation. We have to graph this thing. You only need 2 points to make a straight line. Why do we ever do more? Just to be accurate. But this, it looks like that's good enough. I have my line. They're not asking me to write the equation. I'm not asking myself to write the equation of it. I could. Find the slope. We already know the y-intercept. Okay, this next one here. If I didn't transform it into this, which we'll confirm that this matches it, let's go ahead and find the x-intercept and y-intercept. The x-intercept is found by setting y equal to 0. So if I set y equal to 0 in this equation, let's change colors. I've been using blue for too long. I'm going to get 2x minus 3 times 0 equals 6. Now, this was an unnecessary step to write because no matter what, when I plug in y for 0, this value will go away. It always will. If this is in standard form, this is all you're going to be left with. 2x equals 6. So what do you have left? Divide by 2. X equals 3. So your x value when y equals 0 is 3. So your point on this is 3, 0. That's one of your points. Your y-intercept, without me writing anything for this, your y-intercept, set x equal to 0. -3y equals 6, divide by -3, y equals -2. So what's your point? 0, -2. And there it is. So standard form, you can plot 2 points really quickly, just you don't get as many points. Maybe your thing is a fraction. You can't see it from your number, so you do have to do an actual division calculation. Oh boy, heaven forbid you actually have to do some math work. But, you can still graph this way. Still not my preferred method, although what's great about that standard form is, for the most part, you're given all integers. Slopes just sometimes turn people off. Speaking of which, here's slope-intercept form. Start at 0, -2, go up to over 3. Yeah, it looks like this matches. Okay, last one here, y-intercept, x-intercept. I'll go ahead with y-intercept for this time. Set x equal to 0. This goes away. 2y equals 16, therefore y equals 8. So there's a point on this graph that is 0, 8. Right up here. Here's another one. Set this equal to 0. Set y equal to 0. This goes away. 5x equals 16. X equals, 16 over 5. Now the exact value is 3.2, so it's not impossible to plot. But what if that wasn't that's not a preferred thing to plot there. This is an example of when you might actually do conversion. Solve for y, do slope-intercept form. Maybe you're just a little happier by doing that. So what do you do for slope-intercept form? You solve for y. How do we do that? What was it? 5x plus 2y equals 16. Okay, subtract 5x. And then divide, this is a y. And divide both sides by 2. You're going to get y equals -5/2 x plus 8. And notice I left this as a fraction, not as a decimal. Yeah, that's -2.5. But we like fractions in our slopes. We use it. Down 5 over 2, right? So starting at 0, 8, which we already have that point, we go down 5 over 2, down 5 over 2, etc. So that worked out. It's pretty good. Okay. Another thing about converting forms that I wanted to mention is that you can convert something from slope-intercept form to standard form. You just have to follow the rules of standard form. So let's say I looked at this equation again. Y equals 2/3 x minus 2. And we already know what it goes back to. The rules of standard form, sort of, is that your x's and y's are on one side of the equation. You have a constant on the other side. Everything is an integer, and your x value was positive. So let's say I moved this 2/3 x over to the other side by subtracting. Now, if negative 2/3 x plus y equals negative 2. Okay, two issues here. This is a fraction, and this is negative. So to clear the fraction, you multiply by the least common denominator. In this case, it's just 3. But I'm going to multiply by negative 3 because that way that can get my x term positive. So negative 3 divided by 3 is negative 1. Negative 1 times negative 2 is positive 2. So we get 2x minus 3y, notice I multiplied by negative 3, equals positive 6. So that's standard form. That's converting that way from there. And we know this was 2x minus 3y equals 6, as we saw there. So there's conversion practice backward and forward. Okay, finally, point-slope form. Let's go ahead and write the equation. Y minus y1 equals m times x minus x1 as that quantity right there. Slope formula, wait, what the heck did I write? Oh, slope formula is y2 minus y1 over x2 minus x1. We already talked about what that whole idea is with change y, change in x, and why that gives you this equation here. And converting form is getting from point-slope form to slope-intercept form in case you ever want to. But in converting form, let's just talk about it because we're here now. Converting form, distribute slope into x's. Basically, if you're talking about slope-intercept form, y equals mx plus b, notice how there's only how there are no parentheses. This one has parentheses. So you're going to distribute the slope into x's. You're going to move over everything. You're going to solve for y. And you're going to combine like terms. You're going to simplify it because there normally will be like terms to combine. All right, bad handwriting, but good work. Let's go ahead and do some of these examples and see exactly what it is we're dealing with. Point-slope form. Point-slope form as opposed to slope-intercept form gives you the slope and a point. So in this case now, we have to say what's our slope, what is a point that we're given. We'll do the same thing that we did with the slope-intercept form, only we're going to start at a specific point and not at the y-intercept, unless what we're given is the y-intercept. So our slope is negative 4. There's our m, negative 4 over 1. We're going to apply that with a certain x1, y1 value. The point that we're given, x1, y1, is, remember, y minus y1, y minus 2. Therefore, y1 is 2. So we know that this point is something comma 2. Okay. X minus x1. This is x plus 1. So that's x minus negative 1 if we want to tie it to the slope. So your x1 is negative 1. Notice that when you're adding, it's actually a negative value. So your point that is a solution to this line is negative 1 comma 2. So let's go to negative 1 comma 2 right there. This is a good reference point because we know it's on the line. And then we can apply the slope thereafter. Negative 4 over 1. Down 4. 1 to the right. Remember, negative slope. And so on and so forth. This keeps happening with all these different problems. But the difference here is that, okay, well, we didn't have the slope. But you have the slope. You have a point, sort of. You find out kind of what that is and work from there. Okay, passes through negative 7, negative 4 with a slope of 3/4. This time we have all the information we need. If you did want to write this in point-slope form, this would be y plus 4, right? Y minus negative 4 equals m times x minus negative 7. That's x plus 7. So here's what it would look like in point-slope form. This is the information you get out of it. So how do we do this? Start from your point that you're given and use your slope, 3/4. Up 3 over 4. And so on and so forth. Okay, I'll go do those 3 right there. Perfect. Okay. So that was possibly an easier problem, but that's how we use that. Okay, passes through negative 6, 5, and 3, 1. Okay, we have 2 points this time, but we don't have a slope. So you have to find a slope for this thing. You can find it through the graph if you really want to. You can also use this, y2 minus y1 over x2 minus x1. Let's go and use this because we wrote it. x1, y1, x2, y2. If we do y2 minus y1 is 1. Let's change color again. We got 1 minus 5 over 3 minus negative 6. And that's going to give you negative 4 over positive 9. And that's your slope. It doesn't reduce. That's it. Now, what if we change this to x1, y1, and x2, y2? It'll still give you that slope. Only your 9 will become negative, your 4 will become positive, but that's still a negative slope. That doesn't change anything. So now we have that. If you wanted to write the equation, you'd use that as your slope. And your x1, y1, you can choose either point. You can either choose negative 6, 5, or, what was it? 1, 3? 3, 1? Or 3, 1. And you can plot that into point slope form. I will graph in just a second. Although you should now know how to do it. Come on. So you can do y minus 5 equals negative 4/9 times x minus negative 6. That's x plus 6. Or, I'll put it over here. I don't know why. Y minus 1 equals negative 4/9 times m minus 3. Excuse me, x minus 3. Okay, these are both the same equation. You can graph from one or the other because they're both solutions to the line. The slope will cross through them as long as you start from one and go to the other. Now, they look different, and they do. I mean, like, even to me, they do. If they asked me, look at these without writing anything, determine whether these are the same line, I couldn't tell you. I mean, I couldn't. So that's where we'll talk about converting form. But those are your equations. Let's go ahead and graph. Starting from negative 6, 5, we'll take a slope of negative 4/9. 1, 2, 3, 4 over 9 over 6 over 3. That's over 9. And look, we land at the point 3, 1. So, it must be. Yeah, that must be accurate as far as starting at this point, doing negative 4/9, starting at this point, doing negative 4/9. Of course it is. So maybe you lucked out, right? Now, where does this cross out? What's the y-intercept? Around 2.5, maybe a little less than that. Only reason I'm saying that is because I'm actually going to find the y-intercept for you, and we'll confirm that it's it. But converting form here. All right, converting form to y equals mx plus b. Why might we want to do this? We might want to do this to confirm that they're the same line, right? Or you might want a y-intercept. Distribute the slope into the x's, solve for y, combine like terms. Okay, I have to do this one twice because I want to prove to you that these are both the same numbers. Now, unfortunately, we're going to deal with fractions in the y-intercept and everything and combining like terms. But, hey, it's all part of the practice. So distribute the negative 4/9 into the x and the negative 3. I'm going to have y minus 1 equals negative 4/9 x. Negative 4 times negative 3 is positive 12. So we're going to get 12 over 9. 12 over 9 reduces to 4 over 3. So plus 4 over 3. Okay, now we got to add 1 to both sides. And here's where things get a little, oh no, fractions. These cancel. You're going to do plus 1 over here. 4/3 plus 1. Well, 1 is 3/3. Common denominator. So 4/3 plus 3/3 is 7/3. So your final answer is y equals negative 4/9 x plus 7/3. Which is 2 1/3. So when I said 2 1/2, 2 1/3 is close enough. So there's your equation for the line. This isn't a fun one to graph, right? I said fractions are okay for slope. They aren't okay for y-intercept. So you're really seeing the added benefit of using point slope form. Okay, the other thing I want to do is just confirm that this is the same thing. You get the same slope-intercept form out of this. Distribute negative 4/9 into the x and the 6. You're going to get y minus 5 equals negative 4/9 x. Negative 4 times 6 is negative 24. Negative 24 over 9 can reduce if you divide top and bottom by 3. You're going to get negative 8 over 3. So minus 8 over 3. Add 5 to both sides to solve for y, and then we'll combine like terms again. Plus 5 plus 5. Okay, so we're now going to have y equals negative 4/9 x. Okay, 5 is 15/3, common denominator, multiplied top and bottom by 3. Negative 8, remember this is a negative. A lot of people are going to forget that. Negative 8 plus 15 is 7. So we're going to get plus 7/3. And voila. Proving here that we get the same exact equation. These must have been the same line. They had the same slope. We were so far so good. But we didn't know if they had the same y-intercept. We didn't know if these points were solutions to the same line, given that slope. But you were really asked to graph it. I was still giving you more information that you might need or when you might transform. Very, very, very few times have I ever seen anybody, including myself, transform from slope-intercept form or standard form to point-slope form. It's okay to do. I just don't do it often because you can pick any set of points to use. Okay, horizontal lines and vertical lines. Horizontal lines have a slope of 0. Okay, they are used in like y equals like c equations. You know, f of x equals c. It's a constant, no slope. That's just what's applied. Vertical lines is an undefined slope. I mentioned that. And those are x equals equations. I'll just call x equals c, another constant. So there is no way you can do a y equals equation and get a vertical line. That would require an undefined slope. Even a slope of 1 billion is still not vertical. The only undefined slopes here are x's. Now people get these lines really confused, and I'm not saying that you shouldn't. I understand why, because we think of x as left and right. X goes in the left and right direction, but when you're referring to something like this example here, x equals 7, we're referring to the point x equals 7. 1, 2, 3, 4, 5, 6, 7. Now, it's not a point either. It's still a line. Because what this whole thing is about, let's say we made a table, an xy table, only now y is kind of your independent variable. Plug in values for y into your equation and get values for x out. Y equals 0 in this equation. What's x going to equal? And some people will sit there confused saying, there is no y. Okay, you're right, there is no y. So what should x equal? Well, it's going to equal 7. So we have that point. Plug in 1 for y. What's x going to equal? 7. 2 for y, x is going to equal 7. 3 for x is going to equal 7. So the whole point is no matter what y equals, x is always going to be 7. If y equals 1, 2, 3, 4, etc. Negative 1, negative 2, negative 1 billion. No matter what, x is going to equal 7. So what does that give you? It gives you a vertical line. So right here, we're going like that. Undefined slope. Okay, because there's no run. Dividing by 0 can't do. I understand that. Okay, y equals negative 4 is the exact same principle for the y's, only now you go up and down for y to figure out where negative 4 is. Well, it's right here. There are a couple ways you can do this. The way that I would really go about this if you really had trouble is I would write this in slope-intercept form. It kind of is, but it's missing its mx part. If this is y equals mx plus b, your m must be 0 for your x to go away. So it's y equals 0 x minus 4, y equals 0 over 1 x minus 4 if you like writing fractions for your slope. Your slope is 0, 0 over 1. Your y-intercept is negative 4. Start at negative 4, go up 0 over 1. Up 0 over 1. You're not rising and you're running infinitely. So this one's a horizontal line. So again, no matter what x equals, which literally I can plug in values for x, no matter what x is, I'm going to multiply it by 0. So it gets nullified. And then what do you get? You get negative 4 back out. Horizontal and vertical lines are always perpendicular. You can kind of tell looking at that right there. Talking about opposite reciprocals. Okay, they're opposite reciprocals of each other there. X equals y. This is not a vertical or horizontal line. I'm just throwing it out there in case you're really confused on what the heck this is. Well, don't get too confused by it. Again, one thing you can do is write this in slope-intercept form. Y equals 1x plus 0 or 1 over 1x plus 0. Start at 0, 0. Go up 1 over 1, up 1 over 1, etc. Or you can use a table. And that one's actually probably going to make more sense. X and y. X and y. When x equals 0, what does y equal? Well, 0, because x equals y. When x equals 1, what does y equal? 1. 2, 2, 10, 10, negative pi, negative pi. No matter what x equals, y equals. So they're the same distance away from their respective directions. So it's going to be like a directly diagonal line. As diagonal as you can be, like that. X equals y, y equals x, same idea, but this is also another way of using it. Okay, so graphing recap. Now I'm not done with this stuff. I'm only going to talk about parallel and perpendicular lines after this, although there's a lot to talk about. Every form has a shortcut method to be able to create a graph with little or no calculation. Standard form, you find the x and y intercepts, you plot those points, and you draw the line through it. How do you do x and y intercepts? Set the other variable equal to 0. Y-intercept is x equals 0, x-intercept is y equals 0. Point slope form, you start from the point that you're given. You might have more than one point. You can choose either or, and then apply the slope. Go up whatever, over whatever. Slope-intercept forms the same thing, only start from the y-intercept that's given. 0, comma, whatever it is. Apply the slope. Rise and run. Vertical and horizontal lines, just find the intercept of your value given, then draw perpendicular to that axis. I didn't really say that before, but find the value, 7, draw perpendicular to the axis you're going with. I think that works out, right? You know what I see a lot, and this is where things get kind of goofy. What if you drew your graph this way? You're like, x equals 7. Okay, well, every x equals equation would have the exact same line then. No, this is the line y equals 0. The x-axis is y equals 0. The y-axis is x equals 0. Okay, so that's that recap there. Let's start talking about parallel and perpendicular lines. Parallel lines occur in a coordinate plane when two equations or lines have the same slope and different y-intercepts. Keep in mind, if they had the same slope and same y-intercept, they'd be the same line. So they'd intersect at every single place with each other. So they wouldn't be parallel because parallel lines can't intersect. So you're going to have a test here. Are the following lines parallel? Here's where one of those things come into play where you cannot assume by looking at it. Now, that's kind of a major hint as to at least one of these sets of lines probably isn't parallel. Now, I'm looking at these, and I'm convinced that they're parallel. I made these, and they look parallel to me. So one of these might not be. We'll see which one it is. Let's test red. Now, how do we test for parallel lines? Well, first of all, we see the graphs. We see the y-intercepts. We know those are different. We got to see if the slopes are the same. And that's really all there is to it. So to help you out a little bit and make sure that you don't guess that they're passing in other places, I picked points where these are for sure passing at. Okay, and then you can calculate the slope from there. Now, you can do it using the slope formula. I'm going to expedite this a little bit, and I'm just going to go ahead and do it with the graph. Kind of use the counting principle. I'm going to say how far over did I go, how far down did I go. Those numbers are good enough for me for my rise and run. Okay, this point is 1, 2, 3, 4, 5, 6, 7 away over here, and 1, 2, 3, 4, 5, 6, 7. So this 7 plus 7 is 14. That's how much that's running. How much is it falling? Remember, if I'm going this way, I'm running to the right and falling. If I'm going this way, I'm going up, rising, and I'm running to the left. But I called this a positive 14. So I'm saying I'm running and falling. So I'm going down 1, 2, 3, 4, 5, 6, 7. So negative 7. So right here, I have negative 7 over 14 as one slope. I'll call it slope of 1. Negative 7 over 14. That reduces to negative 1/2. Reducing fractions will be important for this. Because if they're the same slope, for the most part, they're not going to give you the same raw fraction. More so often, they'll give you, more so often, you're going to have to compute what that fraction is going to end up being in the end to confirm that they're the same. This one, falling and running. So this time as I fall, this number will be negative down 1, 2, 3, and over 1, 2, 3, 4, 5, 6. So negative 3 over 6 is the other slope. That reduces to negative 1/2 as well. Are the red lines parallel? Yes. They have the same slope and different y-intercepts. These will never intersect. Same exact rate. Okay, the green one. In the green, let's erase some of this stuff here. In the green one here, we have the exact same thing and as far as what we're going to do. How much does it run? How much does it rise? Yada, yada. Let's check these ones out. Running 2, rising 1, 2, 3, 4, 5, 6. Okay? Up 6 over 2 for one of your slopes here. Okay? Which is 3. 3 over 1. That was about 3. This one right here, let's check this. Run and rise. This is over 1, 2, 3, 4, and up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's 13 over 4, which is 3. Just kidding, it's not 3. It's 3.25. 3.25 over 1, right? These are different slopes. They're pretty close. They are. But eventually, this one, over time, will catch up to this one and intersect with it. If it's a little bit steeper, that means it will intersect. Green, no. They are not parallel. And I am convinced those green ones look parallel. Really, I am. But if I zoomed out more and more, you would see that they're not. All right, write equations parallel to the following lines that pass through the point 4, 1. So what we have to do is we have to understand this thing about slopes of parallel lines. They have the same slope. Okay. So if I'm going to write a new equation that passes through a new point here, I have a couple of options. But the first thing I'm going to do is say the slope that I'm looking for that's parallel to this is going to be the same as this one right here. It's going to intersect at a different place, and we got to find out what its y-intercept is. Or you can use point slope form. You already have a set of x1, y1 values. x1 is 4, y1 is 1. So I could write this equation like this, and there's nothing wrong with it. And by the way, this is a parallel symbol. Y minus y1 equals m times x minus x1. Totally fine and acceptable answer. If you don't want this and you want slope-intercept form, you have one of two options. You can either take this and convert it to slope-intercept form by distributing the 1/4. Not too bad because you don't get a fraction here, 1/4 of negative 4. Or, and do the rest, what we did before. Or, and this is what I often do, I rewrite this as y equals 1/4 x plus b. I say, I know that it's going to be the same slope. I still need to find this y-intercept. Now you're going to use this x and y value, substitute them in, be careful, make sure that the 1 goes for y. Just because 4 is on the left doesn't mean it goes to the left over here. 1 for y, 4 for x, that's a 4, and solve for b. 1/4 of 4 is 1, so 1 equals 1 plus b, b equals 0. So y equals 1/4 x plus 0, or better yet, y equals 1/4 x. That's the equation of this line. This one crosses at the origin. This one crosses at the point 0,5. So they're parallel, and I found the equation of this line. This one looks a lot cleaner than the point slope form, so maybe you go for that, but that's kind of how I do that one. Okay, a line that passes through, something parallel to this line that passes through the point. Okay, to make this work, you're going to have to find out the slope. You can't find something parallel to something unless you know what the slope is. So to do that, let's convert this into slope-intercept form. Subtract 6x. Divide both sides by, oh gosh, those are two y's. Divide both sides by 2, or by 6, excuse me. You're going to get y equals negative 1x, negative 1 over 1x. Let's write that. Plus 1/3, because you really want to know what your slope is. So your slope that's parallel to that is negative 1 over 1. So you know when you do this, you're going to be dealing with that. Yeah, I'll use negative x anymore. So if I'm just going to do slope-intercept form like I did last time, y equals negative x plus b, this is what it's going to look like. Now, they're all variables, but b is what you're going to solve for, and you know that this point is 4, 1. You know that it passes through there. So you substitute 1 for y, negative 4 for x, and you find out what that y-intercept value is. Add 4 to both sides, you're going to get b equals 5. So your equation is y equals negative 1 over 1x, or negative x, plus 5. This is parallel to this one. Different y-intercepts completely. This is a fraction y-intercept. Good thing we didn't have to graph it. But the same slope. There you go. Okay, last example here. Are the following lines parallel? What do you have to do for this? You have two options. Graph them. You can use standard form for this one. That's fine. This is standard-ish form. Find the intercepts. However, remember, graphing them, you can't always guarantee that even though they look the same, they might not be, or the algebraic way, which is, to me, it's just make sure they're both written in slope-intercept form. This is already written in slope-intercept form, so we already know that the slope here is 3 over 1, or 3. So let's see if this one gives us a slope of 3 over 1. Here we go. Solve for y. Add 12x over. You get 4y equals 12x plus 20. Divide both sides by 4. Y equals 3x plus 5. Now, the 5 is still important. It's not just enough to know the slope here, which is 3, so that checks out as well. Both the slopes are 3. But the y-intercepts have to be different. Remember, if the y-intercepts are the same, then you have the same line, so they wouldn't be parallel. That would be almost a trick question, almost a bad, not a bad question, but a really hard question, because you're thinking so much about slope, you forget about the y-intercepts and say they have to be different if they are parallel. Otherwise, they intersect everywhere. So yes, these are parallel. Y, same slope, different y-intercept. Okay, last thing to talk about here is perpendicular lines, and we're going to do the same exact stuff here. Perpendicular lines on a graph occur when two equations and lines have opposite reciprocal slopes. Opposite means different sign. If you take the opposite reciprocal, you change the sign. And reciprocal is take the inverse. Flip numerator and denominator. The opposite reciprocal slope gives you 90-degree angles. Okay. 1/2. If a slope is 1/2, its opposite reciprocal slope is -2/1 or -2. These are perpendicular to each other. In fact, we might be doing a graph that has 1/2 and -2 on it. That's an example of it. So change the sign. Oh, this was written. I'm sorry. Change the sign, flip the numerator and denominator. Okay, are the following lines perpendicular? Red, green. Here we go. Same stuff as I did last time. Red, let's test what these slopes are. Determine, not that they're the same, that they're opposite reciprocals of each other. And if they are, then we validated that thing. By the way, I haven't mentioned it. I don't know if it's mentioned anywhere. But vertical and horizontal lines, as we know, are perpendicular. Therefore, they are also opposite reciprocals of each other. Think about x the slope of the x-axis here as 0 over something. And then y's thing is something over, not equals, y's is something over 0. And let's call it negative something just to be funny. Okay, there's opposite reciprocal. So it still works. They don't really say that for that because there's no true slope for those, for undefined. Anyway, this one here, I'm sorry. 1, 2, 3, 4, 5, 6, 7, down 7 over 1, 2, 3. So your slope for one of these is -7/3. Red over here, let's check this one out. Now, by the way, tilt your head a little bit. They kind of look perpendicular for both of these. Maybe to you one of them doesn't. We'll see. 1, 2, 3, 4, 5, 6, 7, 8, 9. And up 4. So this one is 4 over 9. Now remember, they weren't supposed to be the same. They're supposed to be opposite reciprocals. But the opposite reciprocal slope of 4 over 9 is -9 over 4, which is clearly not what -7/3 is. They're close to the same thing though. -7/3 is -2 1/3. -9 over 4 is -2 1/4. So they're really close to each other, but they're not quite the same. This one's opposite reciprocal slope is 3 over 7. I don't know the exact decimal for that. It's around 0.42, blah, blah, blah. So no, these are not opposite reciprocal slopes of each other. Definitely not. So they're not perpendicular. This is not perpendicular. Green, the green lines, you might expect that they are. Let's see. Let's go ahead and do that slope thing we were talking about before. Draw red with the lines. I think I like that idea. Okay, this one right here. I run 1, 2, 3. I rise. Ooh, it's a little fat. I rise 1, 2, 3, 4. So up 4 over 3. That's a slope. Okay, this one here actually needs to change colors because it's going to intersect with it. It's changed to purple. We're going to fall as we run to the right. So how much do we go down? 1, 2, 3, 4, 5, 6, -6 over 1, 2, 3, 4, 5, 6, 7, 8 over 8. Fall 6, run 8. So you start to look at these and say, no, they're not opposite reciprocals. But don't forget to reduce this fraction. This is -3/4. These are opposite, These are opposite reciprocals of each other. Opposite, sign changes. Reciprocal, the numerator and denominator flip. So these ones are perpendicular. You tilt your head on that green one, you better say those are perpendicular because they are. So yes, green is a resounding yes for that one. So that's kind of the thing. You got to test the slopes. Now, opposite reciprocal, whatever with lines and such, they can have the same y-intercept. These ones almost did, actually, right? Because they will just intersect once, and maybe where they intersect is right there on the y-intercept. Never know. Okay, write the equations perpendicular this time, not parallel, to the following lines that pass through 0, 3. Notice how I use the same equations, only now a different point that's passing through. Okay, perpendicularity. Before, we knew that this slope was 1/4. If we want a line that's perpendicular to it, we need to know its opposite reciprocal slope. If its slope before was 1/4, its opposite reciprocal slope is -4/1, or -4. So everything is the same as the parallel line stuff, even down to you can use point slope form or slope intercept form. The one exception is how you find your slope. So this slope that we're going to use, I'll just use slope intercept form. Y equals mx plus b, so it's y equals -4x plus b. You're still going to plug in 0 for y, 0 for x, 3 for y. And by the way, if you do that, you're going to get -4 times 0, which is 0 plus b, so b equals 3. So your equation is, I know I write all over the place, I don't have much room, y equals -4x plus 3. So that's the equation of the line that's perpendicular to this one and passes through that point. I won't prove it by graphing. Feel free to do it. Even use your graphing calculator. But this line intersects through this point. This one doesn't necessarily do it. In fact, I don't think it does. Okay, there's one. I'm going to go and erase it because I want to get some room for this one here. Number 2, if you will. This is the exact same thing as that other line. Let's go ahead and rewrite it. Y equals -x plus 1/3. Y equals -x plus 1/3. Okay, the slope on this one was -1/1. So the opposite reciprocal slope is going to be positive 1/1. I mean, they're still both 1s, even if you flip them. So positive 1/1. So it's like diagonal here, diagonal here. All right, so now we know that our equation will have a slope of 1. So it's going to say y equals positive 1x plus b, or better yet, just x plus b. We're going to substitute 0 and 3 into this equation here. 3 for y, 0 for x. Not that interesting. You still get b equals 3. So it's going to be y equals positive x plus 3. And there's that one right there. Yeah, and that's perpendicular to this original line or perpendicular to this transformed line. They're both the same line. But here you can clearly see opposite reciprocal slopes. Awesome. Okay, last thing. Are the following lines perpendicular? Same idea as we were talking about before. They have to put this into slope-intercept form, figure out if the slope here is the opposite reciprocal of the slope here, and then you're in good shape. Then you say yes. It doesn't matter if the y-intercepts are the same or different. They can be the same. Keep that in mind. Okay, solve for y. 7y equals -21x. We subtract 21x from both sides. Minus 14. Divide by 7. Y equals -3x minus 2. All right, there's nothing here that screams opposite reciprocal. In fact, you might accidentally answer yes because you said, oh, they're the same, and you forgot they were talking about perpendicular. These lines are actually not even close to perpendicular. They're parallel. These are parallel lines. So the answer here is no. If this was, which it's not, if this was positive 1/3 x minus 2, then yes, these would be perpendicular because opposite reciprocal. Remember, -3 is -3/1. Here's positive 1/3. But that was not the case. It looked like this. Answer is no. All right, so to summarize everything, we discovered how to find the slopes of lines. Rise over run, delta y over delta x, y2 minus 1, any of those. Counting measures, rates, reducing fractions. Write linear equations given points on lines and their slopes. All right, so we did a lot with those forms, and we found out how to write those equations with that. How to find x and y intercepts given the equation of a line. Substitute 0 for y when solving for the x-intercept, etc., especially in standard form. How to use slope-intercept forms of linear equations to sketch graphs of lines. That was probably the first thing that we did, right? Start with the y-intercept, rise over run, this and that. And how to use slope to identify parallel and perpendicular lines. Once again, same slope, opposite reciprocal slope. That's it. Fiend.